Imagine if your pills had a brain, knowing exactly where to go, how much to release, and where to stop. That's exactly what polymeric nanocarriers do. They're like microscopic pharmacists, making sure your medicine works smarter, not harder.
Nanocarriers are very small particles which are designed to carry our drug to the site of action and also to protect it from the acids and enzymes that are in our bodies. Nanocarriers are usually between 1 and 100 nanometers. Well, when 1 nanometer is 1 billionth of a meter. And when we think about the fact that we can fit 100 million nanocarriers in 1 centimeter, we begin to comprehend how small they actually are, which makes it possible for the cells to take in the complex. Fact number one about polymer nanocarriers is that they can be more easily modified than lipid and metal carriers in order to achieve biocompatibility and targeted drug delivery. One of the molecules that is being investigated is hyaluronic acid. Hyaluronic acid is a sugar-based molecule naturally found in connective tissue like joints. And when we add methacrylate groups to it, we make it easier for the molecule to undergo polymerization, which is what we want from a manufacturing point of view. One of the drugs that can be delivered with the polymer is adenosine, which is used to treat osteoporosis. Since the site of action is the bone tissue, when we conjugate hyaluronic acid methacrylate with another molecule, alendronate, we make it easier for the carrier to bind more strongly to the bone tissue. And one of the advantages is that the bonds between adenosine and the carrier are reversible. So this feature can be exploited to improve control drug delivery and reduce side effects.
Nanocarriers can improve targeted drug delivery. Nanocarriers are specific and allow for targeted drug delivery through many mechanisms. In this video, we are going to be discussing the two main mechanisms, passive and active drug targeting. Passive targeting delivers drugs to its target by conjugating with the polymer. The nanocarrier then releases the drugs outside of the target cells in a phenomenon called the permeability and retention effect. For instance, let's think about this. Tumor cells have abnormal blood vessel structures and they display as leaky due to the gaps between their tissues. This structure then allows the passive diffusion of larger molecules like nanocarriers into tumor tissues. Smaller nanocarriers can penetrate better into the tumor membrane, evading immune recognition, which will allow the drug more time to circulate into the bloodstream, making it more effective. Active targeting is done by attaching targeting agents like antibodies and peptides that recognize specific biomarkers to receptors overexpressed on the surface of target cells, like cancer cells. This mechanism then can greatly increase the drug uptake in the target tissues. One study even showed that active targeting was twice as effective in delivering the injected dose than passive targeting. Both our passive and active targeting mechanisms play different but crucial roles in nanoparticle-based drug delivery systems. Passive targeting employs the unique physiological structures of a tumor, while active targeting uses drug receptor interactions to increase the effectiveness of drug delivery.
Fact number 3. One of the key advantages of polymeric nanocarriers is their ability to release drugs in a controlled manner. This means that drugs can be delivered at a steady rate over time, which helps maintain therapeutic drug levels in the body, which will also reduce side effects that could be caused by peaks or variations in the concentrations of released drugs. For instance, researchers have developed stimulus-responsive polymeric nanocarriers, which can release drugs in response to specific internal or external triggers. Internal triggers could include changes in pH or the presence of enzymes, while external triggers could include light, heat, or ultrasound. This makes them particularly useful in targeting specific areas like tumors, where their environment is different from healthy tissue environments. This can also enhance therapeutic side effects while minimizing harm to healthy cells. For example, in 2021, a study developed polymeric nanocarriers with PFC core that releases drugs when triggered by ultrasound. It found that low-frequency ultrasound around 300 kHz effectively activates stable high boiling point nanocarriers to release the drugs. This means that we can direct drugs exactly where it's needed using ultrasound, which will enhance treatment precision.
Now a break from our regularly scheduled programming.
Normal drugs are like tourists who get lost in a new city. Polymeric nanocarriers, they're like the tour guide that gets them straight to the right spot, no detours or distractions.
Fact number 4. Polymeric nanocarriers come in a diverse range of structures, from micelles and dendrimers to nanogels and nanocapsules. Each stand out due to their unique structures and functionalities, and each one of them is tailored for improving solubility, targeting specific sites, and enabling controlled release. For a quick overview, micelles encapsulate hydrophobic drugs benefiting cancer therapies. Dendrimers offer precise drug encapsulation and targeted delivery. Nanogels respond to environmental stimuli for sustained drug release. And finally, nanocapsules provide controlled drug release with a protective polymeric shell. These nanocarriers are a promising tool in modern medicine as they enhance precise drug delivery and therapeutic performance.
Just over 20 nanocarriers have been approved over the last 30 years, most of which are liposomal in nature. Of those, no polymeric nanocarriers have specifically been approved by either the FDA or the EU authorities for medical use. Although medicines that may bear some similarities, which make use of a polymeric gel matrix to slow drug release exist, for example, the drug Eligard, used for the treatment of prostate cancer and uses PLGA or polylactic glycolic acid, which is considered a candidate for use as a nanocarrier material due to its biocompatibility and biodegradability. It appears that issues with scalability and control over reaction parameters has been an issue for polymeric nanocarriers, and this, along with batch-to-batch variation, is likely responsible for these drugs not having yet reached the market.
To conclude, here's a quick recap of all the nanocarrier facts. Fact number 1. Polymeric nanocarriers have a flexible composition which increases targeted drug delivery in diseases. Fact number 2. Nanocarriers use specific mechanisms for delivering drugs, such as passive targeting that allows drugs to penetrate through the tumor cells, and active targeting that allows drugs to bind to the cancer cell's receptors. Fact number 3. Polymeric nanocarriers allow for stable and controlled drug release, which will reduce side effects from releasing drugs gradually over time. Fact number 4. Polymeric nanocarriers come in many different forms tailored for specific uses like micelles and dendrimers. Fact number 5. Currently, the use of nanocarriers are approved by the FDA and the EMA, with over 20 nanocarriers being approved up to date. Thank you for watching.